Hello and welcome to this look at how to do typical exam questions in A-level chemistry to do with graphs and rate of reaction. It's primarily aimed at first year students. So we'll be looking at things like how to draw tangents, how to draw different shaped curves when you change the reaction conditions, that sort of thing. This is the main part of the question where you've got the information plus the data, and I'll bring up each section of the question that relates to this as we go. So the first thing is to draw a labeled diagram of the apparatus you would use for the experiment. So it describes a gas syringe, and the diagram just needs to be fairly basic like that, with the gas syringe labelled. The idea being that you've got a sealed container, and you've got a piece of glass tubing coming out of it, maybe with a bent at right angles, or maybe a rubber tubing. It depends on how you might have done this yourself. But it doesn't really matter so long as it's fairly clear that this is the kind of setup you're going to use. The next part of the question wants you to draw a graph of volume of gas produced against time, and then state what happens to the rate as the reaction proceeds and explain why this happens. So what the mark scheme wants you to do is have labelled axes, correctly plotted points, and a smooth curve. So this is what I did. I'm not 100% sure about my curve up here. It could be a little bit better, but I'll go with what I've done. And then as the reaction proceeds, obviously the rate of reaction goes down. As you can see, the gradient of the curve gets less steep. The reactant particles are being used up until the limiting reagent, which is HCl, runs out. I know that HCl is the limiting reagent because it says that zinc is in excess, so the other reagent must be limiting. And finally, collisions between reactant particles become less frequent. So notice I'm using A-level language this time round rather than GCSE language. So then they say, use the graph to find the rate of reaction after 5 minutes and after 9 minutes, and then show by calculation that the zinc is in excess. So taking our graph again, we draw a tangent at 5 minutes, and we do dy over dx. So this line here just shows that the dx equals 7.2 minutes. I'm using the x-axis to work out what my dx is. That gives me roughly 9.17 centimeters cubed per second. So to work it out after 9 minutes, you do something similar, except my tangent is at 9 minutes. And that gives me 1.6 centimeters cubed per second to the -1. So any marking of graph-related answers would depend on individual tangents drawn and therefore be flexible. So to work out that the zinc is in excess by calculation, you first of all work out the moles present for each reactant. So you have 0.0306 for zinc, that's mass over molar mass. And then for the HCl, which is a solution, it's N equals V times C. So that gives you 0.01 moles. So looking at the equation, you can see that it's a 1 to 2 mole ratio between the zinc and the HCl. So the zinc is in excess because the zinc that would be required to react with 0.01 moles of HCl would be 0.005 moles, which is significantly less than the 0.0306 moles of zinc available. So the final part asks you to calculate the volume of hydrogen you would expect to be produced. The molar volume of a gas is 24.8 decimeters cubed at room temperature and pressure. So for the first one, you end up with 124 centimeters cubed. Now, the reason we're using 0.5 times the number of moles of HCl used is you can see that there's a 2 to 1 mole ratio between the HCl and the hydrogen gas. So we've already worked out that there's 0.01 moles of HCl, so therefore the number of moles of hydrogen will be 0.005. So multiply that by 24.8 and you get 124 centimeters cubed, or 0.124 decimeters cubed. Now, physically, when you're doing this practical, you start the reaction and then you have to put the bung back into the reaction vessel. During that split second, some gas might have escaped. So therefore, although we predict 124 centimeters cubed, we actually ended up only getting 118, so there's not quite so much. So finally, then we need to sketch on your graph and label the curves you would expect for each of the following changes. So rather than draw them onto my graph, I've done a sketch electronically, and you can have a look. So basically, my original curve is the orange one, and the curve for 6A is for 2 grams of zinc and 100 centimeter cubed of 0.1 mole per decimeter cubed hydrochloric acid. So half the concentration, twice the volume, same number of moles. So therefore the curve levels out at the same place. And for 6C, there are more moles, same moles, I beg your pardon, because you have the same values, same volume, same concentration as up here, but it's a 50 degrees C, so it's hotter, so the rate of reaction is going to be faster, so the curve is going to be steeper. I'll leave you to have a think about what the curve for 6B might look like. Okay, thanks for listening. Until next time, see you soon.